Welcome to the Explainer. All right, if you're looking for a highly structured visual breakdown of chemical reaction efficiency, you are exactly in the right place. Today, we are tackling one of the most universal and frankly frustrating mysteries in chemistry, the missing product. We're going to map out exactly how and why chemical reactions pretty much never go exactly as planned, and how you can absolutely master the math behind it all.
Picture this. Have you ever followed a recipe perfectly? Let's say you're baking a cake, and you've measured every single ingredient down to the gram. But when you pull it out of the oven, it's only half the size you expected. Where did the rest of it go? Did some batter stick to the bowl? Did it spill over the edge? Well, that exact same frustration happens constantly in the chemistry lab. You rarely, if ever, get as much physical product in your beaker as you originally calculated on paper. So today, we're going to unpack exactly why that happens and visually label the mechanics behind this major pain point for your lab practicals and O-level exams. Okay, here's our roadmap for today. We're starting off with the missing product mystery, then exploring stoichiometry as our chemical recipe. From there, we'll break down equations and mole ratios, move right into calculating percentage yield, and finally, wrap things up with avoiding common mistakes. All right, part 1. The missing product mystery.
To actually solve this mystery, we first need to make sure we're speaking the right language, and that language is stoichiometry. It's the quantitative language of chemistry, used to predict exact amounts of reactants in products. Think of it as your flawless micro-level recipe. It completely anchors our understanding, because these underlying molecular rules directly dictate the macro-level physical results that you are actually measuring on a scale in the lab. Now, as we map this out step by step in our flowchart, notice that before you can predict any yields, your absolute first step is to balance the equation. Why? Because of the law of conservation of mass. You literally cannot create or destroy atoms, you're just rearranging them. If your starting foundation isn't perfectly balanced right here at step 1, every single calculation that follows is going to be completely off. Moving on to part 2, stoichiometry, the chemical recipe. And that takes us to part 3, equations and mole ratios.
Let's break down a real example, the combustion of propane. The equation is C3H8 plus 5O2 yields 3CO2 plus 4H2O. I want you to trace the relationship between the reactants here. For every 1 hidden mole of propane, you need exactly 5 moles of oxygen. See that? That 5-to-1 mole ratio directly acts as your precise conversion factor. It's basically the fixed bridge allowing you to cross from one substance to another within a reaction seamlessly.
Which brings us to the core of it all. Part 4. Calculating percentage yield.
This split screen right here is the ultimate showdown. It's the heart of our entire explainer. On one side, we have the actual yield. This is physical reality, right? It's the imperfect, slightly messy powder you physically scrape out of a beaker and weigh on a lab scale. But on the other side, we have the theoretical yield. This is pure perfect theory. It's the exact maximum number you calculated on paper using stoichiometry. Honestly, understanding this boundary between the messy reality and the perfect theory is the absolute key to everything that comes next.
So here's our master equation. Percentage yield equals the actual yield divided by the theoretical yield multiplied by 100%. Every single time you see this formula, I want you to mentally stamp the physical, real-world reality onto the top variable, actual yield, and stamp your perfect, pristine paper calculations onto the bottom variable, theoretical yield. You are quite simply dividing reality by theory just to see how efficient your reaction actually was. Let's apply this to a real scenario to see it in action. Notice the scale of these 2 bars. That first bar shoots right up to a theoretical expectation of 10 grams. That's our perfect paper calculation. But look right next to it. Our actual physical reality stops short at just 7 grams. Really focus on that distinct visual gap between the tops of those 2 bars. That gap literally represents the physical mass that was lost to spills, incomplete reactions, or side reactions. So, doing the math, when we plug those numbers into our formula, 7 divided by 10 times 100, we get an efficiency of 70%. That stark physical gap we just looked at, that translates exactly to a 30% loss during the physical process. You only captured 70% of what was theoretically possible. Let's run through this sequence one more time with a totally new scenario. This time around, our flawless math tells us we have a theoretical yield of 20 grams. However, after actually doing the experiment, scraping the beaker, and measuring out the powder, our actual yield sits at 15 grams.
Once again, we divide reality by theory. 15 divided by 20 times 100 gives us a 75% efficiency result. Notice how the physical dimension of your yield always drops when it crosses from the perfect theoretical whiteboard into the very imperfect physical lab.
And finally, part 5, avoiding common mistakes.
Now here's a massive red flag for you. Can your percentage yield ever go over 100%? The answer is a hard no. Absolutely not. If you run your equation and hit 105%, you can't magically create more product than your starting atoms allow. It's chemically impossible. This immediately guarantees that a structural error has happened somewhere. Either your lab equipment was wet or contaminated, which artificially inflated the weight, or you accidentally flipped your variables in the calculation. If you see over 100%, stop right there and recalculate.
Okay, let's do a rapid-fire recap to really lock this in. First up, stoichiometry relies entirely on precise quantitative relationships. Second, a flawlessly balanced equation is unconditionally your first step every single time. Third, those mole ratios, they are the fixed conversion factors you use to bridge different molecules. And finally, percentage yield is the ultimate metric. It measures your actual, messy lab efficiency against your perfect paper theory. Every single point here builds a clear, logical connection from the micro-level math directly to the macro-level lab results.
So as we wrap up, I want to leave you with this provocative thought. Have you double-checked your mole ratios for your next exam? The most successful students out there don't just memorize formulas. They practice tracing these sequences with different scenarios until it's practically second nature. Run the actual versus theoretical numbers forward and backward until you can spot an error a mile away. If you found this visual breakdown helpful, make sure to hit subscribe so you don't miss our next structured deep dive. Keep learning, keep questioning the math, and I will see you in the next explainer.